Okay, our next speaker is Bruno El-Bennich, Departamento de Física, Universidad de Sao Paulo. Bruno, thank you very much for attending our event. The next talk is about transverse quark distribution in hadrons. Bruno, you have 1 hour, including time for question or comments, okay?
Bueno, buenos días. Yo creo que algunos todavía quieren terminar el café, ¿no? Primeramente, muchas gracias por invitarme. Creo que sea mi 7ª vez en Colombia, mi 2ª vez en Pasto, de esta vez con mucho más fortunato que la última vez, porque casi me perdí aquí en la pandemia. Y aquí, entonces me alegra mucho revisitar este lugar en condiciones mejores. Y en particular quiero... estoy muy feliz de visitar a todos mis amigos, Eduardo, Carlos, Carla, Herman y todas las otras personas que no había visto en mucho tiempo. Bueno, a la vez la charla voy a hacerla en inglés. Yo creo que es un poco más fácil para mí y también, que es normal, también para los estudiantes, lo digo también que estamos en Brasil, nosotros organizamos un seminario semanal con los estudiantes y todos tienen que presentar en inglés, porque al final es importante cuando se van fuera para un postdoc y todas esas cosas, tienen que entender las cosas, ¿no? So with it, I'm gonna switch to English. I work in Sao Paulo, in Brazil, where I met Eduardo many years ago, actually more than 10 years now, right? We're getting old. And it was 12 years ago. 10 years ago, I came the first time to Tolima, where Carlos organized a workshop. And we have had many Colombian students and postdocs over the years, and I keep working with some of them over the time, so I come visiting. One of my collaborators here, so these are collaborators. Some do the work, some lead, some don't do nothing, like me. But in general, nothing is done alone. So speaking of this, unfortunately, one of my good collaborators, actually Fernando Serna, he moved back after doing his PhD in postdoc in Sao Paulo to do the Sucre in the north, close to Barranquilla, no? Or Cartagena perhaps. He's been working there, but he couldn't come. He's too busy. So these are the people. Adnan just gave the first talk, and I've been working with him also probably for the past decade or more on things like quark-gluon vertex, our collaborator in the US, where I spent some time. As you can see, it's a very international and a very Latin American collaboration, so I will present parts of bits of over the years from probably some things I will not have time to present. So Javier Cobos from Mexico, my colleague in Sao Paulo, Orlando Oliveira, who gave us a lot of lattice QCD input for Green's function, and with whom we work too. Don Rojas, whom you know very well, the local. Fernando Serna, Roberto Silveira, and of course we have also a paper with Carlos, but I won't talk much about these results today. I'm going to talk more about more recent things. Okay, Roberto is my student, he just finished his PhD. So let me find first some motivation. So when I learned that I actually should give a longer talk, I thought I'm going to give a more specialist thought. So like, okay, if this is a long talk, probably I should talk a little bit more about experimental. I always think experiment at the end is the first thing that should motivate us as a physicist. So I'm going to talk a little bit about, not about past, but about future projects. In particular, the new electron-ion collider that's going to be built in Brookhaven National Lab. It's a bit of an extension, a much modern, a much more potent, and with high resolution version of the current Jefferson Lab in Virginia. And it has been approved. We got a CD3 critical decision. That means the government approved the budget, said you are allowed to start building, and they approved the design of the building. So that's going to probably going to start building this year, I think, and probably the first runs in 1932. So it's going to be probably the prime accelerator in the US. And so one of my missions is a little bit to motivate, and at the end of the talk I will come to this, we wrote a white paper, is to motivate the high energy and the nuclear physics community to not look only at CERN, but also other accelerators. There will be new ones in China and Japan. There's much more than LHC going on. I don't want to talk, I love LHC and CERN, and I've worked on flavor physics too. But so let me give you some motivation, and especially for the students, probably the first 20 minutes I will give a bit like Adnan, but Adnan actually set the stage and made my life much easier, speaking already about QCD and the history. Maybe I'm gonna do a little bit more popular talk here in the first slides and talk about a couple of things that motivate me and hope can motivate people here in Colombia, like in Brazil too, in the future, in participating or contributing to this physics. Okay, so this new collider will be a 2 4-point-mile circumference world-class particle collider. Basically, it's going to be on top of the previous RIC accelerator, right? So that was the Hadron and the heavy ion collider that stopped running with the STAR collaborations, other collaborations in Brookhaven National Lab that was doing heavy ion collision experiments. And so people in the community 10 years ago, more than 10 years ago, decades ago, of course, gathered and said like, okay, we have a laboratory in Virginia, we have one in New York, and as always, we want something bigger, but you won't have money for 2 times something bigger. So the basic people have to join and like, okay, what's the next physics we want to learn about? What are things that people come from Hadron physics? What are people come from high energy nuclear physics who want to learn about quark-gluon plasma? At the end, people want to learn about confinement, deconfinement, understand actually Hadron structure, because as Adnan probably hope conveyed to you, even simple things like a proton, which we suppose are simple, are actually very complicated objects, and we still have a lot to learn about it. If you are just a nuclear physicist and you don't care about the internal structure of a nucleon, you just say, okay, I want to know how this nucleon interact within a big nuclei, fine. But understanding how from quarks, from the QCD Lagrangian, we can actually build a proton, the mass, it's what gives mass to the proton. It's 3-dimensional distribution, it's excited state, it's a weak interaction, it's electric interaction. There's still apparently, not only apparently, there's still a lot to learn and a lot to study, even for beyond standard model physics. Okay, so it's gonna be this circular ring, and you're gonna have photons who can collide directly with protons. So in this ring, you prepare here basically your ions, your nuclei, and they go in one direction, and the helix is going in the other direction, and basically you'll hit, okay? So this is all what we know, right? You have a nuclei, inside you have a proton, and the naive picture from the 60s, 70s, 80s is basically you have 3 quarks, they interact with gluons, but the thing is there's a lot of stuff happening around there, a lot of stuff, because as we learned yesterday, in the talk about the first plenary talk about neutrinos, empty space is not very empty, okay? And the deeper you hit, the harder you hit with your photon, the more it's like with a microscope. You're gonna discover that inside this proton, there's a whole sea of quarks, antiquarks, of gluon. This ocean is what gives actually the mass to the protons and to the nuclei, actually to us, our life, right? Because 3 quarks, as I will argue very shortly, the mass in the standard Lagrangians of the 3 quarks doesn't explain anything about the mass of our nuclei, atoms, molecules, DNAs, etc. Fine? Okay, and so the AIC, its purpose is to explore that in a microcosm, with a much higher resolution than nowadays. So it's not going to be at very high energy. People don't try to break up things or produce new particles. They just want to have a better microscope. It's much, much higher resolution to understand what is the glue in there, especially how the glue, these particles that supposedly have no mass, contribute to the masses of the hadrons, not only the protons, all the hadrons. Okay, so head-on collisions of high energy protons or nuclei to reveal how the inner building blocks build up the properties and structure of all visible matter in the nucleus. Because we can write a Lagrangian, that's good. We've done this 50 years ago. Adnan told you we celebrated 50 years of QCD. Very large momenta, very large, collision of high energy. We can do perturbative QCD, but the Lagrangian won't tell you how to actually calculate the properties of a hadron, right? There's no hadron, there's no proton, there's no pion, there's no eta, there's nothing in the Lagrangian. So the origin of mass, right? 70s, 80s, the experiments, simple experiment from SLAC, the first deep inelastic scattering experiments, revealed that, we heard this before, Rutherford scattering, protons or nucleons in general are not elementary particles. They have an internal structure, These return structures, if you calculate cross-section and you look at that, then you see that you had the Bjorken scaling, for instance, and it shows that this behave like little points inside this big sea, or with this big basically cake of a nucleon. And so people were very happy with this story, because in QCD with a color algebra, you can show they can form a color neutral objects out of 3 colored quarks. You know how they interact. And then you have this kind of Mercedes star here, and you think, fine, that's the end of the story. People were happy. Oh, the quark model in QCD, we don't really know how, why the proton is so heavy, because compared with a quark that is 5 MeV. But okay, it was, for a while, this was good, right? But then this was all with experiments in the 90s and 2000 with the event of Jefferson Lab in particular, but also DESI in Hamburg and other labs and experiments. People got a high resolution. So they actually, the deep energy scattering got to larger Q square value, larger momentum transfers. Also looking at transfer momentum transfer and increasing a lot the resolution of the detectors. And the interior structure of a proton can be much more complicated. So you don't have only these 3 quarks, you have this whole sea of other particle things. So that's a little bit of a headache, especially if you want to do a calculation. I want to calculate, for instance, a wave function of protons. So what do? I can't only use 3 quarks, I have to use all of them. How do I calculate, for instance, a wave function in quantum mechanics or in quantum field theory, because it's a relativistic problem. So the next thing is the origin mass. Why do I write this? Adnan hinted at it, right? If you look at hadrons themselves, you just take the quarks that are inside, supposedly, for instance, a pi, a quark, antiquark. Then you take a proton with 3 quarks, and you take the masses of them that you have in the Lagrangian, you add them up, they don't make 1-2% of the proton mass, okay? If you introduce the dynamics of the gluons, how everything connects and how everything interacts, then you can actually find, this was probably the most important piece of work in the last decades, with lattice calculation, and now slowly also using GPDs and everything to extract the gluon contents of the protons. People realized that actually most of the masses in our hadrons, in our nuclei, and in our molecules is not due to the Higgs mechanism. So the Higgs mechanism, it was an amazing event. That's also some 12 years ago, right, when LHC announced it. But it's wrong to say, or to assume that mass is due, visible mass, I'm speaking. We saw yesterday, what we deal with is actually mostly with our ignorance. We know visible mass, but even of this visible mass, most of it is not due to the Higgs mechanism. The Higgs mechanism is an important mechanism, but chiral symmetry breaking is dynamical. So it's due to interaction. Interaction, as you know from relativity and from Einstein, energy, radiation is mass, right? The famous E is equal to mc squared. So, as I said, what creates the alternating? So this is probably the biggest motivation. There are many other things. Spin problem, there was a spin crisis. There were many other motivations to understand better nuclei and the spins of nuclei, the spins of hadrons, how they actually, because once you admit that a proton is not only made of 3 quarks, so what contributes to the spin? Angular momentum, the gluons themselves. There are many contributions, so it's not that easy a task. It's not that easy anymore. Once you admit that this is a relativistic quantum field theory problem, it's not just a simple quark model with 3 quarks. Oh, 1/2, 1/2, 1/2, I add up and then I get either 3/2 or I get 1/2. No, it's much more complicated. So this electron-ion collider will take 3-dimensional precision snapshots of the international structure of the proton atomic nuclei. It's like really a more sophisticated way what people have been done since SLAC in the 1960s with a high resolution, and of course, snapshots with also much high resolution, which of a shorter time, right, in the interaction. Taking images as a range of energies, this EIC will reveal features of the ocean of gluons and the series of quark-antiquark pairs that form when gluon interacts. Okay, so more than you will now the dynamics between these 3 constituent quarks, or what makes actually these light quarks and the Lagrangian constituent quarks. And so we can map out with this the particle distribution movement within proteins and nuclei, similar to the way medical imaging technologies construct 3D dynamic image of the brain. What we're doing, basically, especially the software, it's an inverse problem. The software from the data, you analyze this data and you reconstruct an image, right? You don't have a direct image. Nobody has a lens there or a camera. And that uses actually mathematical models and inverse problem methods that is known also in tomography. Basically, that's the reason also people speak here of three-dimensional tomography of hadrons. So all these efforts hopefully will reveal how the energy of the massless gluons is transformed through E = mc squared to generate most of the mass in the visible universe. And we know this is still a modest share, but at least, if we can explain this small fraction of our visible mass, I think this would be within the next 20 years, 30 years, especially for the young people. I will probably retire by then. But for the younger people, this could be a great motivation. And it probably doesn't sound as exciting as beyond standard model physics, but it is an extremely, extremely sophisticated problem. The simplest distributions, which I will start with, are, okay, let's forget, for instance, for now, the transverse motion. Just say, okay, you hit the quark with a photon, and by this you kick it, and at very, very large momentum, so the quarks inside move at a speed which is close to the velocity of the speed of light, and neglect for now the transverse motion of these quarks. Just say, okay, it's just moving longitudinally, and as I will show very shortly, then we assume a framework, or basically a frame in which the particle is basically just along this light front, okay? And so it's just a light front reference frame, and we will just look at it as the quark carrying a fraction of a momentum in the infinite momentum frame. So you basically imagine you go to a system which is boosted along, for instance, the motion of the quark, then you can actually forget the transverse distribution. At the end, I want to come back, because obviously we are not at infinite momentum, we are something realistic in experiments, and so we are interested in the transverse motion. But let's start with this simpler distributions. So, as I said, you know this all from probably undergrad. In relativity, time and space, of course, are unified. It's a four-dimensional space. Of course, you cannot represent this here, you have to simplify it. So you have a past light cone and future light cone, and we live here, always in the hypersphere of this present. So this fantastic physicist, this genius many years ago, Paul Adrien Maurice Dirac, in the late 40s, worked actually on different reference frames, and where you can define the physics, coordinates. And it's not just a coordinate change. Actually, when you quantize your field theory in different frames, he actually proposed three ones of this. The instant form, which is basically the one we know, right? The one is given like c squared, t squared minus x squared would be basically you're on the light cone, it's just 0. And then he proposed another framework, another reference frame, and he introduced what we call nowadays light front coordinates. So basically, the transverse pair doesn't change. We just mix time and space. So x0 would be your regular time in Minkowski space. x3 would be just along the z direction, right? And the z direction would be the peripheral direction where you kick your quark, where it's basically moving along. I have two ways in one dimension to do this, plus and minus. And this x plus is interpreted as, in this reference frame, the new time variable, okay? And x minus just plays a new variable which belongs to the other three coordinates. Doing this, right, we define a light front. So light cone is actually, Adam spoke about this. What are wave functions on the light on the light front? So many of this one-dimensional distribution I will talk about are normally known as light cone distribution amplitudes. But as Brodsky himself said, this is sort of a wrong terminology because we are on the light front. Once you define these variables and you find the light front x plus 0, that's similar to what you do usually when you're on the light cone, right? You define c squared times t squared minus x squared is 0. So you're on the cone. Here, you're basically on the front, and the physics you want to describe is this here on the front, always at a time at this time-space separation, x plus equals 0. So this one is 0, okay? So why would you do this? I would have to probably have a lecture series just to explain why this is beneficial to Hadron physics. It turns out that when you quantize in a field theory in in the light cone frame, certain things complicate because you break symmetries, especially translation or rotational, because you introduce a preferred direction, right? The light cone. However, the vacuum simplifies drastically. And in a nutshell, what this means is basically because everything is at the speed of light, right? If you have, then you have your fog, for instance, in your fog space, right? You have your states, your fog states. And then you can show that you quantize within this reference frame, the vacuum is very simple. So basically you can forget about this whole sea of gluons, quarks, everything, and your fog states, basically, your nucleon is just really 3 quarks, or your meson is a quark-antiquark state. The problem is, up to today, is really how do I derive this, a constituent quark mass in this light from framework directly from the QCD Lagrangian. But in a certain sense, it has an advantage, because if I'm in Minkowski space in my front form, I want to know, for instance, what's the probability to have one quark has that much percentage or that fraction of the momentum of the proton. I can't answer this in a normal frame, because there are infinitely many particles. Quantum field theory is an infinitely many particle theory. So I cannot say, oh, it's 30%. 30% of what? Right? If I have infinite many particle and proton, I can't say much. There's no probabilistic interpretation. This framework has the advantage because the vacuum, in a certain sense, is trivial, although there are debates about this. Also, it is not free of criticism. It simplifies a lot the interpretation of Hadron physics. So I can have really a probabilistic interpretation. So light cone distribution amplitudes, what are they? They're called LCDA. As I said, it should be rather than light cone, it should be light front. They were introduced many years ago, in the late 70s, early 80s, in the context of perturbative QCD calculations of hard exclusive reactions, okay? And particularly of factorization. So basically, when you have a cross-section, you factorize the perturbative part, and you can show actually to leading order, next to leading order, that there is a perturbative kernel that multiplies some functions, which are the wave functions, the distribution amplitudes of the mesons, of the hadrons in general, in this scattering, okay? And that's pretty nice, because if you can factorize this, and people always seek to do this in QCD, you can show, okay, one thing I can calculate to certain precision, higher precision. I can test even maybe beyond standard model physics in. The only thing is somebody has to give me somebody who does non-perturbative field theory, lattice QCD or a functional approach to Dyson-Schwinger, has to give me a wave function. And preferably on the light front, because that's where most people work in these QCD approaches. There are scale-dependent non-perturbative functions, scale in a certain sense that they obey evolution equations. In particular, later we will see with the PDF, they obey D-Gleb equations, Dokshus, Gribov, Lipatov, then I always forget the fourth name. Dokshus, Gribov, Altarelli, I think. And that's important. These here also obey evolution equations by Brodsky. The page, then there are 2 other names. I always compare them. Maybe I should just write them. So that means it does matter, like the running of the strong coupling. It does matter at which scale you observe things. Okay, in any field theory, scale or basically distance matters. That's usually you have the renormalization group equations. You can just say, okay, this is my coupling, this is my mass. No, they all evolve. They all depend on the scale you're observing them. And the scale also will have to deal, it's not a one-to-one, it's not a trivial relation, but it will have to do at what momentum you probe, for instance, the quarks within these hadrons. So for instance, where do these things appear? I think this could be of interest. I've worked for a while on this, and I know some people here are interested in flavor physics. This distribution impedance of B mesons, but also D mesons, contains information about the probability of finding the light quark within a certain momentum fraction inside the heavy meson. You need this in calculation. I'll show in the next slide where does this wave function enter. In the light front frame, X is basically, so K plus is what I showed you before. It's a light front frame, it's a momentum of the quark and its plus component in this light front frame divided by the total light front momentum of the hadron. Okay, so it's basically a fraction. X is basically, and you can relate it in the fast-moving, in the fast-moving frame to the Bjorken X. Okay. So where does this enter? Weak decays of heavy mesons. I have here some pictures, for instance, of B mesons. I mean, this has been studied at Babar, in Slack and Stanford, at Keck, the Bell experiments for many years. Nowadays, it's studied at HCCB, and there's, of course, a Super Bell also in Japan. So this has to do with the quark sector of CP violation. Okay, so this is kind of related, or very strongly related, to measuring basically the CKM matrix elements, and understand, or better, what are the sources of CP violations in weak decays in these hadrons. So these hadrons, for instance, can decay, a B can decay, for instance, a pine and a rho, and there can be obviously sub-decays. And now what you see, this whole mess, I can say something in QCD factorization about the vertex, where this weak decays, about the quark physics. But you can see, that won't help me much if I don't understand everything that happens here, there, if I don't know the B wave function. And worse, even if you have actually three body final states, because all this is hadron physics. There's no weak physics. The whole weak decay happened here. The new physics happened here. But this is all blurred by a lot of hadron physics. So you really have to get this under control. So let's go a bit more. Let's zoom in. What happens? So this would be probably here somewhere here. Okay, here I have only strong decays. I took a case which is here, for instance, semi-leptonic. That means at the end you have a hadron, or a meson in this case, and a pair. It can be, of course, mu plus, mu minus. It could be also electrons. It could be taus. And of course, especially this particular decay is quite interesting for people who are looking at anomalies for a while. Some people are sitting here, right, Eduardo? And what happens here? Well, you have something that's called the penguin diagram. So quark, of course, emits a W boson. It's absorbed again. So you change flavors. You have the CKM matrix elements here. And of course, there are many diagrams. It can be a photon, it can be Z boson. There will be also some diagrams where gluons are basically radiated, and they create either lepton pairs or quark pairs, or quark anti-quark pairs here. But in this case, what happens here in these loops can hide a lot of physics we might not know, and people study this intensively. Here we have standard model physics, at least we believe so. So we have here the wave function of a B meson, and on the light front, in this reference frame, these are basically the light cone distribution amplitudes. So, more mathematically, where do they enter? This matrix element, for instance, here you have a B, and it decays, for instance, in, that's like the most, one of the most famous decays, because this is one of the first that was probably observed and studied much in detail, in 2 pines, pi plus, pi minus. This happens, of course, if you do heavy quark effective theory via vector VA, vector minus axial vector currents, so Fermi currents. You have basically here 4 quark operators, and there's all kind of operators that contribute, right? Because every diagram, there are different ways of weak decays, and actually you need more than one way to decay to have CP violation, because it's interference that will reveal this CP phase. And so in QCD factorization, in perturbative QCD, you can show that this basically can be represented by integrals, convolution integrals, where you have a hard scattering kernel. So this you can calculate. It gives rise, you do basically have a quark effective theory. It gives rise to Wilson coefficients. You take matrix element of quark operators, etc. This is very well under control. People have calculated this to 2 loops, 3 loops. People calculate all kind of beyond standard model contribution to this. Now, what you have here, as you see, are distribution amplitudes. So this is one distribution amplitude. You can see that everything here, basically, you neglect in a certain sense because the quarks are fast moving. You don't consider here transverse motion. You can do this. People have actually done extension of this work. Then you have transverse motion. It gives rise to pseudocurve reformations and all kind of other effects. But in essence, you can also write it just like this, right? And as you see, for all initial and final states, you have distribution amplitudes. This probability amplitudes of how much momentum the quarks carry inside their hadron. So this goes back to work of Brodsky-LePage, very famous work. You can actually do something like in quantum mechanics, right? What you have when you have a wave function, you solve your Schrödinger equation, you do an expansion usually, Legendre polynomials. You want to basically separate always the momentum, or k squared, p squared, from the angular dependence. And you can do something similar here, right? As expansion. Here you don't have an angular expansion because this is just one-dimensional. But you can write it in terms of polynomials, and those are the Gegenbauer expansions. So you have moments here. And of course, if you keep only the first one, you can show that asymptotically, this would be for large mu squared. If you go to infinity, right? Like taking alpha s, for instance, strong coupling or other things, at very, very large momenta, all these coefficients here, these momenta are suppressed. Those are polynomials. It's just basically Gegenbauer polynomials of certain order. Meaning this has to do that in the conformal limit of QCD, wave functions basically are expansion of this. But you could also use other polynomials. That's not, this goes basically back to work of Brodsky-LePage. So the only thing I want to tell you is that at really asymptotic, and when people said asymptotic, they really meant infinity. These people are, these moments, these contributions are suppressed, and what is basically surviving is a 6x 1 minus x, okay? And up to today, many people for the longest time in this calculation have just used this asymptotic form, but that is not even warranted at large NSC like at the LHC, okay? When you can plot this, you'll see a symmetric function, has a certain width, and what I will try to convince you, if you do realistic calculation, the width will depend a lot on what state it is, at what scale, and it will can basically sort of expand. We'll have distribution that are much broader or much narrower. So you have to be very careful with this expression here. Okay, so it has accelerated scales. This is just simply not true. You can't use this. So therefore, motivated by flavor physics, but also by perturbative calculations in other exclusive or reactions, many people for the last 20, 30 years were, of course, after the LC days. And as I told you, you can write this as an expansion, and the expansion and you can calculate moments of this expansion. And so that's what, for instance, lattice QCD we worked very hard on for the last couple of decades. And for a long time, there was nothing, but now improved iteration, especially by German groups, but also some groups in the UK, have calculated the first two moments for pi and kaon. That means the first two moments we know in this expansion up to a certain order. So it's still far from knowing the whole light cone distribution amplitude. Okay. Now this was for the light mesons. For B mesons, it's still a big challenge for lattice QCD due to spirit energy scales, because you have various scales. If you have the pi, you have these scales, you have the quark mass scales, and that's fine. But if you have B mesons, you have very, very different energy scales. I mean, you have the heavy quark, you have the light quark, you have lambda QCD, and so that means you have to do things on a larger volume, but with a very fine spacing, and that's very costly to do on lattice QCD. And so this, to calculate directly, this has been really, really a tough problem. And people make current progress with something that's called large momenta effective theory. So you basically boost to a frame where this becomes easier, okay? If you boost basically to a very, very large momentum frame, and then you can actually, you have less scales. You can simplify your problem, because if your PCs goes to infinity, you go actually close to a frame where you have your hadron mass, which is a B meson mass. This, of course, they enter light cone distribution amplitudes and then many things. This Adam showed this already. If you do this calculation, so this is basically the old calculations of Brodsky-LePage. Nowadays, what Adnan showed, you don't limit yourself to one-dimensional calculations. You actually consider the transfer motion. But if you do this just in a not simple, but in a in a framework that neglects transverse motion, you have basically the pine form factor, and you can show this is work by Brodsky-Lepage, that, you know, Q squared, this pine form factor, basically behaves like the weak decay constants times alpha s, of course, at a certain scale, okay? And so in the light contribution enter here in this calculation is same, for instance, in what also Adnan showed, is basically a transition form factor, right? A virtual photon, two photons create a pine, right, via the anomaly. But nowadays, what people are much more interested in is basically GPDs. So the GPDs, Eduardo asks this. No, nobody has actually measured them for now. This has been for the last 20 years probably the most sexiest or the most in fashion distribution. There's no warranty nowadays that we can really measure them. There are many, many approaches and methods show that this will probably be possible. It's a construction, a much more generalized construction of PDFs, because it includes the transverse motion, includes the longitudinal motion, and includes a scale variable that describes basically the momentum transfer. So those are very sophisticated distribution, which you can actually derive from something that's much more general. Those are the Wigner distributions, right? And basically, Wigner distributions is what is the phase space of this whole thing. Now, people want to do actually vector Mason photo production. So you'll have here, for instance, the light cone distribution. And with this, once we understand these objects, and we could measure them, then calculation exists. They exist in basically in simple quark models. Lattice calculates some momenta of them in sort of effective fields, so it's not really in QCD. And also in Dyson-Schwinger approaches have been applied to this, but with many simplifications so far, because it's a very complicated problem, right? This is basically, you have a nucleon coming in here, nucleon coming out there, so this is a many-point Green's function. The thing what you want to do this, and this I'll discuss very briefly, is by creating these mesons, it will interact with gluons, and with this you can actually test the gluon content inside the nucleon. So this is quite a very important experiment. But more importantly, besides doing this, the GPDs are related to other distributions, namely the Parton distribution functions and transfer momentum distributions, which Parton distribution have been already measured, and transfer momentum distribution functions I think will be not a problem to measure. This will be experimentally probably very successful. And the GPDs, I think there's still some criticism, but experimentalists are very optimistic that this can be achieved at the IC. So another distribution functions, what I told you before, this light cone distribution amplitudes, they're just wave functions. Like in QCD, wave function, like in quantum mechanics, wave functions are what they are. They're not physical objects. You cannot measure them. They have a complex phase, right? Because there's the Schrödinger equation gives you complex solutions. So this is nothing you can actually measure. They enter, however, in decays, in transition amplitudes, and if you take the amplitude squared, then you have actually a probability interpretation. This is in quantum mechanics. And here, it's in this light cone frame, this is very similar, because now my Fock space is much easier. I can actually do a probabilistic interpretation as in quantum mechanics. So the PDFs are actually measurable compared to the light cone distribution amplitudes. They're actually measurable objects, and they enter in cross sections, okay? So they have to do with deep inelastic scattering, and where you actually define pattern distribution. This goes back also to the 70s, 80s, when people looked at deep inelastic scattering and, of course, at cross section. So you assume again a fast-moving hadron, and a piece of jet of particles moving in the same direction and sharing its total momentum, okay? So you have an electron coming in, it hits a quark, and basically you shake up this hadron very strongly, for instance, a nucleon, and then you look what's happening. You know, you're breaking something out. If it's elastic, of course, you're not breaking something up. But any of these partons, right, if you go back to Feynman's picture, carries a fraction x of the momentum on the light front, or in general, right? And now you hit this, and so you have to basically sum over all possibilities that the photon hits up one of the constituents, one of the partons here in your nucleon, your initial nucleon. And this will be, of course, a sum, and you have to integrate over all possible fractions, right? Because one quark, you don't know this, right? You have to sum basically over all possibilities, that the quark, each of the partons, each of the quarks inside the proton can carry that much of a hadron's momentum. Okay. When you do this, your cross section, you can write it basically like this: the sum. Actually it's an incoherent sum, so it's not this modulo squared. It's an incoherent sum of each of this scattering section of each of the individual partons squared times the probability over which you integrate. And that defines basically the parton momentum distribution, okay? I mean, this is for instance, the elementary cross-section or differential synchrotron for this process. But then there's also this resist particle. And then, of course, this you have to take into consideration that can happen as any value of x, okay? And so this f is just basically the probability, dp divided x. And when you, of course, integrate for one, right, for one of the partons and sum over all partons, this must be 1. Because the total probability that any of the constituents carries a fraction of momentum, if you calculate it with sum of all these fractions, of course, altogether the partons added will give you the hadron momentum. In this case, for instance, the nuclear momentum. So this defines the probability to find a part with light momentum fraction k plus over p plus, right? And you can also relate actually how people do this. You don't measure. What you measure basically experiment structure functions of the nucleon, and with those are the Cullen-Gross relation. So if you measure F1, F2, you can extract this parton distribution function. So you don't measure them directly. What you measure is always structure functions of the hadrons. So now the idea is here, I gave you a little bit of an overview, and probably I stretched my time too much. How do you, we have a lot of distribution. Can I unify this? If I want to calculate something in approach, I can calculate, of course, always PDFs can be calculated with diagrams. There's several different, there's always one, as Feynman said, you should have more than one way to do physics. And there are different ways to approach this with different techniques, diagrammatic approaches. The one I want to show here is basically, I can calculate in a relativistic quantum field theory framework a wave function, okay? And if you have a two-body state in relativistic quantum field theory, you use a Bethe-Salpeter equation. Okay? And the Bethe-Salpeter equation is basically summing of all possible interactions that can happen between two bodies. It can be in QED, it could be the Bethe-Salpeter, of an electron-positron, it can be the Bethe-Salpeter of a quark-antiquark, of two quarks, of three quarks, then it becomes a Fadev equation. It doesn't matter. What we have here is basically, initially, if we can calculate this, basically the wave function, the relativistic Poincare covariant wave functions, how do I get to, for instance, this last distribution I have here, this PDFs, which is a distribution that depends only on x, a momentum fraction of the light fronts. So what you do here, I have written this schematically, you project this first onto the light front. You do this with a Dirac delta function. You can calculate momentum. And then basically projecting means, wait a minute, you did this, okay? You have to basically go to light front variables. Then you have a light front wave function. Now I'm in a different framework. This usually you do in Euclidean space with functional methods like the string equation, or Green's functions, for instance. The Green's function, people don't in lattice QC don't really calculate bound states. They look basically at eigenvalues of Green's function. You project this, you have something that depends on x, on the transverse momentum, and then I can do several things. I can either integrate over the transverse motion, I get the GPDs with a certain overlap representation. I can calculate in a different way, not always using the overlap representation, over K perp, and I get distribution I showed you at the beginning. Those are wave functions. I can calculate from this also, take this modulus of squared, I get something that's called transfer momentum distribution. And if I calculate this, because this is modulus squared, so this is something I can observe. This is a probability, right? This is just a wave function. So the transfer momentum distributions are the probability amplitudes, and if I integrate again over K perp, I get my PDFs I just discussed in the last slide. So that tells you what is the difference between PDF and light cone distribution amplitudes. These are basically unobservable wave functions. These are actually probability amplitudes I can extract from an experiment. For instance, the structure functions of nucleons. So how do you calculate this? Burkert, G, and Yuan, that's more than 20 years ago, showed that QCD emissions, there are two independent light front wave functions for the leading Fock state, right? Remember I told you the vacuum is simpler. If I go to the light front, I have basically two Fock states. Of course, they can combine, I have a quark, anti-quark, they can combine to spin 0 or spin 1, certainly. And so you can write this in the sense, so basically here you have quark, anti-quark, basically if you quantize your theory, they act on vacuum. You have basically this ladder operator. I don't want to go detail, but what is important is I have basically a light from wave function for angular momentum 0 and for 1, we call them C0 and C1. And what has been shown is that you can extract this directly from a Faraday amplitude or from that describes a 3-body bound state, for instance, a nucleon, or from the beta sub beta wave functions of a 2-body bound state. So if you do this, these two wave functions, you can see, because what you take here is basically to trace over the beta sub beta wave functions. Don't worry, I will show you how to calculate this later with different, of course, projections. So gamma plus gamma 5 would be, it's very similar to gamma mu gamma 5, which would be the weak decay constant. It's on the right front. And here you can see, right? This x is k plus over p plus. You do this integration. So you integrate basically over k plus and k minus, certainly, and then you have something that depends only on x, right? Because I eliminate k plus, and then I integrate over k minus, and then I have something that depends only on this kind of Bjorken factor and the transverse motion, certainly. And I can do this in two ways. Here you have the sigma plus. Basically, if you look at this, just gives you basically orbital angular momentum or the spin, right? And this is the leading Fock contribution to the pine. And you can go beyond this, of course, because that could be a gluon contribution. That could be, for instance, a gluon state to higher Fock state. But that's the simplest configuration. Now, I've told you all this, my whole motivation. I can actually coming to the meat of my talk. How do you calculate this? I told you, very nice. I want to know about mass. I want to know probability distributions that the experiment is going to measure. But at some point, I have to start calculating this. I can't just, I can go around it for a long time. At some point, I need to calculate these things. So all we're going to use is a functional approach that Adnan already discussed before. So I don't work with lattice QCD. I work with functional approaches, which are based on Dyson-Schwinger equation. So basically, you derive equation of motion directly from the QCD functional, and you can derive from this all kind of Green's function: 1-point, 2-point Green's function, 3-point, which is the quark-gluon vertex, or gluon vertex, etc. And why is this? Well, let's go back to the QCD Lagrangian. Okay, this would be basically the one that gives you, for a non-interacting quark, for a free quark, this would give you just a Dirac equation for the quark, right? This has basically just the interaction term. The no interaction term is just basically the quark fields, but QCD is more complicated, right? You have this interaction term, so in a covariant derivative, you would put these two together, would give you the covariant derivative. And if it were only this, QCD was like QED, quantum electrodynamics, right? You just have basic quarks interacting with photons, and that's it. QCD is more sophisticated. It's a non-abelian gauge theory. So basically, the field's anti-commute, and with this, it gives you a much richer theory, right? So these are the field tensors. A are the color indices, right? And T2, so you basically have here the generators of a SU3 quantum field theory. So it's a bit more complex and complicated than QED. And the key to complexity in QED lies in the fact, I messed the word, that the gluon field strength lies in the gluon field strength tensor. This part, this additional part that we don't have in QED. Basically, you see here, this will give rise to the gluon propagator, so the dynamics of the gluons, right? But here, look at this. Those are structure functions in the adjoint representation of QCD, and you have here a coupling between two gluons, okay? And if you think that you put this in back there, that means these two gluons will interact with other gluons, with a third gluons, or with a fourth gluons. So this makes a hell of a difference with QED, where photons were not talking to each other. It generates self-evolution with far-reaching consequences for Hadron morphology, and we will see this will be the origin of mass. Interacting particles have energy. Energy, according to special relativity, is mass. So this complexity affects the quark-gluon vertex in a non-partitive manner. So this thing too, right? You all learn, this is my QCD Lagrangians. the interaction of two quarks, right? You have quark fields here, you have a gluon field here. It's just gamma mu, right? When you write a Feynman diagram, you would radiate a gluon, you would just put gamma mu. That's true at very, very large energies. If you do hadron physics, this is not true anymore because you will have dressing. So, again, relativistic quantum gauge field theory, interactions may be it in QED and QCD by vector boson exchange. Vector bosons are perturbative massless. You have a similar interaction in QED. The special feature of QCD is that you have these additional vertices, 3 gluon vertex and the 4 gluon vertex. And that, the far-reaching consequences you see already in the coupling, right? QED, the coupling rises very, very slowly, logarithmically, of course, but very slowly over a large range of momentum, okay? QED is an abelian gauge theory, so, actually at large momentum, it becomes non-perturbative, and at small momentum, it's perturbative. Now you add at least the 3 gluon self-interaction, you take a similar quantum field theory, gauge field theory, but now the interaction is due to non-abelian structure of this field theory. When you do this, and you've probably seen this, then a coupling is very different. First of all, right, it moves, the coupling varies much more rapidly on this domain of momenta. And that what Abnan talked about is that the coupling at large momentum, right, of course, is scale dependent, vanishes, it goes to very small momentum. And it's this region where you can do perturbative QCD, because you always know, you do perturbation theory, or like whether in quantum mechanics and a field theory, to resum your effects and be sure that you don't make a big error, you have to have a small coupling. The physics we're interested in happens more in this regime. So this is actually extraction from experiments, deep inelastic scattering, and what I'll show later is this coupling actually was shown in the previous year to saturate. So it's infrared. That's really, really important because it means that QCD is infrared and ultraviolet safe. There's no Landau pole, so it doesn't diverge. Right? So completely different behavior of this. You have something that falls off and becomes, at large momentum, becomes perturbative, but at small momentum, it's non-perturbative, right? This has to do with this. You have a gluon at the screening, right? And you have a fermion screening. In QED, you would have only this. And that means also why, see the sign. The sign is different in a abelian gauge theory than in a non-abelian gauge theory in the beta function. Of course, as Adam mentioned, this gave rise to the 2004 Nobel Prize in Physics, Gross, Politzer, and Wilczek. Extremely important results from the 70s, and that's the reason we're celebrating, or we celebrated last year, 50 years of QCD. So asymptotic freedom, here valid. QCD becomes non-perturbative mainly for Q squared, up starting 2 and at 1 GeV, really, really don't use perturbation methods. So where does this all mass come from, right? I mean, I have the Higgs mechanism gives me just the masses of the quarks, right? If you have looked once at the PDG, the renormalized quark masses in your Lagrangian are of the order to 3, 4, 5, depends on which scale you're looking at, MeV. Now you know that the proton is 980 MeV, or 9 times 10 to the minus 28 kilo. So the interaction, of course, the gluons, once you switch them on, they will contribute this, right? So the dynamics of gluon, right, create 99% of the proton mass. Okay, if I have just the quarks, this is much. If I took just the quark masses, I would just add up to 1%. So where does this hadron's mass come from? After all, the Higgs boson isn't doing the job alone. It is a seed, you need it. So as I said, the gluons interact with each other and have infinite ways to interact with the quark and dress it. Okay. So how do we sum up these infinite interactions? In principle, I could do this also in perturbation theory, right? If you use the renormalization group equations, you can add up, people have worked with this. If you do the RGI equations, you can basically sum up infinite diagrams. But those are still perturbative diagrams. Look at this, for instance. I have the quark propagator. And this is textbook thing, right? You go to Peskin Schroeder. He does it in QED, but in QED very similar. You could calculate this one loop. You can repeat this. You could have 2 loop calculations. Do whatever you want. You can have polarization diagrams. If you could calculate this in perturbative QCD, what you end up is, of course, logarithmic divergences, right? So you have logarithmic contributions, it's normal. Quantum field theory is logarithmic divergent, a leading term, but doesn't matter. If my mass, my Lagrangian mass of my light quark goes to 0, then all this is 0, okay? I will not create mass. But I wanted to show that I don't even need the quark, right? Most of the corrections should give me mass, even with a light quark having no mass, in principle. So in the chiral limit, there's no way I can contribute or create, basically, a constituent quark mass scale. And even if I have a light mass here, light quark mass, all these corrections summed up will not give you what you call now, for instance, in the quark model. So this is, of course, hopeless. And so let me go briefly of what we do. We use different tools based on the Diciembre equation. So in classical mechanics, you have the principle of least action, right? You get the equation of motions. You learn this in Goldstein, for instance, the book. And you obtain a set of equations without the Euler-Lagrange equation. The simplest case basically gives you the Newton's equation. In quantum field theory, you can do the same, principle of least action. You minimize your action in quantum field theory. You obtain equations of motion, and that's for any quantum field theory and for any kind of endpoint functions. It doesn't have to be the quark. And what we get here is something, for instance, if it's in case we do it for the 2-point function of the quark, we get the quark gap equation. And as Adam said, the product can be obtained from QCD's quark equation, and we call this the Dyson-Schwinger equation because it's derived in a functional approach for the rest Fermi self-energy. So I wrote it here in QCD, but you can do the same in QED. And it involves a set of infinitely coupled equations because it really adds up, but in a non-perturbative way, all possible interactions the quark can have with itself. To give you an idea, written as this, the Dyson-Schwinger equation is a nonlinear equation. You have basically here the inverse of the quark propagator. You have normal perturbative, the free quark, and you have something which is addressed Fermi self-energy. As you can see, this term here is basically this. And most students who look at it for the first time, but this is a one-loop calculation. No, senores. This basically is the inverse, and it appears again here. So to know the solution, to get the solution, you need to know the solution, right? This is the fully dressed quark propagator, so it's a solution. This is the inverse one. This is the fully dressed quark gluon vertex, and this is a gluon propagator. Each of them satisfies themselves, right? Like the quark, I can write a gap equation for the gluon. I can derive in this functional approach I can derive the equation of motion for the 3-point function of a quark going in, quark going out, and emitting a gluon. And this thing is a very complex system of a tower of integral equations because each of the 2-point functions involves 3 and higher point functions. So if you calculate one, you need to always know, for instance here, this is a 2-point function, but you need to know the 3-point function, which is the quark-gluon vertex. Here you would need to know the gluon-gluon vertex also, etc. So this is a very tough problem. And because of this, and if you solve this, you have the solution. Adam showed this, you have a quark propagator. This would be the wave functionalization. At large momentums, it becomes just 1, and that would be your current quark mass from the Lagrangian. But this thing is, of course, now something that is more complicated. Like your coupling, it is not something constant. The mass depends on which scale you're resolving it. It's a running mass function, the same way as alpha S coupling, and everything is running basically in relativistic quantum field theories. As I said, you can do this for different, for instance, for the gluon obeys its own Dyson-Schwinger equation involves the ghost, which I haven't talked about. So this, as you say, this very complex set of equations, and all of these equations are coupled, right? The ghost gluon, the quark gluon vertex, etc., with this quark propagator I showed before. And that goes into Bethe-Salpeter equations. So we need truncation schemes, but that actually respect symmetries. I can sit down, but I will have the same problems as in lattice QCD. If I want to resolve it, at some point, in lattice QCD, you have to work with finite volume, you have to break symmetries, but you try to do this in the best way possible, right? And here too, I don't, translation variance, rotation variance, I keep everything. I can go directly to the chiral limit, I have all these benches, but I have to throw out some part of things. I will resum certain infinities, but not all. It's impossible because, if I could do this, I could solve QCD, and nobody hopefully claims can do this. So I may have to make approximations. Still, I want to be guided by QCD. So any DC describes an infinite tower coupled integration equations. Endpoint functions I showed you involve n+1 and higher green function. That's the reason it's a tower. You know, I can calculate this, but inside this there will be higher green functions, like involving 3, scattering of 3 particle, 4 particle, 6, etc. The kernel of the equation for the quark self-energy involves the dressed gluon propagator, this one. So this obeys its own Dyson-Schwier equation, and the dressed gluon vertex. If I simplify this and this truncation, we call this truncation, must preserve essential deterministries of QCD, in particular chiral symmetry. And one thing that has to be always be respected is the axon-watt walk diagonally, so that in chiral limit the pi must be harmless, massless, not harmless. The leading quantitation is simply only bare structure of the quark gluon vertex kept. I keep a dressed gluon, and basically the gluon dressing and this bare vertex together gives me an effective model, but I can resum this infinitely many times in a non-perturbative approach. That's not just perturbative QCD. This leads in a certain sense to planar diagrams. You can actually make an analogy with large QCD. You calculate this and you use an effective dressing, and this effective dressing, you get it from lattice QCD. So this is the dressing function, this, right? In Landau gauge, you have a gluon propagator, and that would be the dressing function. Of course, this is just 1 over q squared. If you go to large momentum, this would be just your perturbative gluon propagator. This dressing function, as you see, goes to 0 and has a very, very fast rise at around 1 GeV at the Hadron scale, and then it saturates. It's infrared safe. Okay? And this has been the object of decades of study now and controversies. For analytical applications, because we simplify our quark gluon vertex, we will use a function or something that reproduces this, parameterizes, and make a model out of this, okay? And if you set this in your Dyson-Schwier equation, you get this. Your mass function, I showed you before, right, is now momentum dependent. It's running. This is done for several flavors. So even the chiral limits, if I put 0, remember when I showed you this perturbation resummation? If your mass in front of the whole sum of these brackets is 0, the whole constituent quark mass, the whole mass goes to 0, all correction. Here, even in the chiral limit, I start with a current quark, basically with a chirally symmetric Lagrangian. But due to the interaction of the gluon, I achieve a sort of a constituent quark mass scale, right? Start with 0, and if you look at this turn of 300 MeV. And the rapid rise, again, like for the gluon, is around 1 GeV. You have this inflection point, it rises and saturates. You have this here for the strange quark, and we call this dynamic chiral symmetry breaking. Okay, you go from a very light mass scale to a large momentum to a large constituent quark mass scale at small momentum. Okay, and of course the effect. This is so what you basically see here. The Higgs mechanism is irrelevant almost for light quarks and becomes stronger for heavier quarks, right? For instance, this is a logarithmic scale, so even for the charm quark, it makes about a 50% difference. For the B quark, of course, the effect of dressing with light quarks is not so important. So, of course, for B, and especially for the top quark, the Higgs mechanism gives all of its mass. All right, so I have to cut it here. Because now let me show some results. So I think I'm going to go a bit faster, because I want it to be two direction. Basically, the same way you do the whole resummation for the 2-point function, for the quark propagator, you have to put it in a quark anti-quark, and you solve a Biddy-Salpeter equation, and you have to do the same truncation I do here. I have to do there also, right? And we do this Euclidean space. We calculate Green's functions, very similar to what we do in what people do in lattice QCD. You have to do this, then basically you have complex momentum, and that has some technical problems, but over the years we have achieved to overcome this, right? In the leading equation would be just a rainbow of truncation with an infinite resummation with dress. So you have basically a dress gluon, but you have a simple vertex here, and that would give the ladder. So you basically forget about cross diagrams. So you solve your Biddy-Salpeter equation for bound state, your quark anti-quark. This shaded area means basically all possible area interaction you can have. You can interchange one gluon, you can have cross diagrams, this, you could have all possible things. For now, what we work with is something that we exclude this, keep the leading diagram, and in an effective way, we keep the dressing, basically, the quark-gluon dressing of basically in the gluon exchange, okay? So the vertex dressing, we say basically, we show this part is important because a heavy quark interacts differently with a gluon than the light quark, okay? For heavy quarks, actually, the dressing is suppressed. For light quarks, dynamical current distribution is much more important, so we cannot throw this in, okay? I won't go into the technical details how to do this. So once you do this, of course, you have the pines are much more richer. They have actually, basically, for pine, for meson, retro quark, anti-quark state, you have a full Lorentz invariant structure with a regular gamma 5 that you know from quark models. But the solution of beta sub beta equation in a fully covariant calculation has other amplitudes. So this is the full beta sub beta amplitude, and that's much more complicated because, for instance, in a non-relativistic quark anti-quark calculation, your parity dictates basically is dictated basically by the angular momentum. So if you have a meson, pseudoscalar scalar, L is 0. Okay? The only possible way to have a state that has negative parity would be L equals 0. In a realistic quantum field theory, that's not true because you actually take into chaos of spin. You could have L equals 1. And that's actually really important, especially in the form factors calculation that Hadron discussed. At low momentum, probably this will dominate. But the quarks are also in the P wave inside because they can, of course, spin 1. And spin 1 and P wave, again, do give you a total angular momentum of 0. In non-relativistic quark models, you don't have this possibility. So I will not go into details. We can calculate the mass spectrum. Maybe just to show you very quickly, if you do this, a lot of this work has been done. This is basically reviewed, improved work of what I did with Eduardo years ago. You can see you can get the masses and the weak decay constants of pseudoscalar mesons. Those are the error compared with experiment, and you can see that it's actually pretty close to experimental values. Weak decay constants, especially in the heavy sector, this is a bit more complicated. There are actually hadronic effects, and also, well, there are no experimental. We compare basically this relative error is compared with lattice QCD calculations. You can do the same for vector mesons. And now I want to show you basically a couple of results. Again, the light front wave function I showed you before, you project like this. I can calculate from this. Once I have this, I can calculate modulus squared. I can get probability amplitudes. This would be the transfer momentum distributions. Integrate over transfer momentum, I get PDFs. And let me show you some results to finish, because I've been probably trapped in too much introduction. This would be the transverse distribution functions, for instance, of a pine. As you can see, it's very symmetric. It falls off very quickly with transverse momentum, okay? This is k squared. So where it's almost 0, this is probably around 700, 800 MeV. Those are symmetric functions and fall off. You have an inflection point, and it actually turns out that the inflection point is almost everywhere the same for all kinds of mesons. Now, if one of the constituents is a little bit heavier, for instance, a squared, you can see this is not symmetric anymore. It shifts a little bit to larger x simply, and you see this even more for the D meson. And for the B meson, it's almost like a peak. It has to do with the fact that the heavier quark carries more of the momentum, right? So the probability that the heavy quark, the B quark or the C quark carries more of the momentum is higher. It doesn't mean that the light quark doesn't have a probability, but it's less probable than in a pine, for instance. If you do this, for instance, here for the BC, and then you see the larger actually the masses are, the more structure you have actually also in transverse momentum space. And that will be interesting to see the difference between, and that is, by the way, all unpolarized, so we haven't taken into account spin. Those is for the eta C, for the eta B, and you can say it forms a large, long, very rich, so the physics here is much more, is much richer than, for instance, what happens for the pine, okay? And if you calculate this for infinitely heavy quark, this would basically, and you know this also from heavy quark effective theory, this basically distributions would basically become a delta function, a Dirac function. Now, if I do integrate over the purpose of the transverse momentum, I get my partner distribution function. The black one would be just basically the asymptotic form. And you can see, so this is basically taking this, right? and I integrate. I project this on this x-axis, right? I integrate over the transverse momentum. When I do this, I get this for the pion, okay? I get this for the kaon. You can see clearly it shifts to larger x, the peak. And this is the whole picture. This would be basically, again, this thing here. That would be, for instance, for quarkonia. Quarkonia, of course, is symmetric because they're made of BB bar and CC bar. So each of the quarks carries like probabilities to carry the momentum of the meson. And then you, for instance, you have this very asymmetric states, like here, for instance, the B, the BU, and the BS mesons, and they peak very highly at very large momentum. But yesterday, we started also late. So this would be light from distributions. These are not the probability amplitudes. These are not the PDFs. Just to tell you, this would be the distribution amplitude, okay? This is for vector mesons. For the rows, and in this case, you have actually transverse and longitudinal distribution amplitudes, and you can see they're very similar for the row, but very different for the K star. The longitudinal one here, we compare with lattice, and actually for the transverse, you see much more this asymmetry, while for the K star, even though it has different quark masses, the longitudinal one is relatively symmetric. This is the lattice QCD result. This shaded band is a Japanese group lattice QCD. The blue one is ours, so we're very happy because we reproduce actually, or we agree with lattice QCD in terms of this asymmetry of the transverse momentum distribution of QCD. This was done with Fernando Serna here from Colombia. Very nice work 2 years ago. This would be for heavy mesons. You can see this, of course, also. It becomes sharper and sharper. The peak becomes higher and higher if you go to larger momenta. This would be for the J psi, for instance, and this is very important, for instance, in vector meson productions to calculate GPDs. And let me come to my conclusions because Carlos looks very nervously at me. Much progress was made from QCD-based modeling towards more sophisticated truncation that preserves symmetries. We obtain non-predictive quark propagators and anti-quark bound states for flavored mesons. They satisfy chiral symmetry and Poincare covariance. Of course, we have to truncate. We throw out quite a bit of physics, but actually for the light meson sectors, and especially for equal mass mesons, this is works pretty well. So this reproduces, or what we showed you in our approximation, reproduces very well Shamonian, Botonian, D and B mesons. The mass spectrum, the weak decay constants, also excited state, I haven't talked about them here. The three-dimensional momentum landscape, right? So with transverse momentum of light and heavy mesons is obtained from different light flow projections of these wave functions. So we don't involve any calculation of the diagrams. You need to know basically the beta sub beta, and calculate the light from wave functions. You don't calculate diagrams. People who use this, for instance, want to use this in flavor physics, we can give them parameterized expression. They can just basically throw it into the, calculate something perturbatively good, calculate the weak B decay constants. I want to calculate beyond submodular contributions. I need an input for my PDA, for my distribution amplitudes of the B mesons region. You can take it from there. And this is the current progress. Improve beyond leading correlations in BSE kernel. So we want to go beyond what we're doing now. And moving on to GPDs and gravitational form factors. And of course, at the long term, what you want to do, you prepare all this. It's a long path to prepare nucleons, which are more complicated because you have 3 quarks. So this calculating bound states of 3 quarks is much more complex when you have 2 quarks. And with this, I want to thank you, everybody, and apologize. Thank you for your patience. I apologize the fact that I went far beyond. I just want to do a little bit of advertisement at the very end, because this really concerns all of Latin America. Adnan is also involved in this here with me and certain people. From Colombia, so far we have only Fernando Serna. We'd like to have more. The idea is, this was a white paper we submitted in September, is trying to create a network of people interested not only in hadron physics, but in particular interested in the forthcoming electron ion collider. And of course, people work, they have collaborations with Mexico, people work in small groups at their own universities with students, but to create a network and share each other's insights and create also a network that has funding. That's more important. Network is fine when you write over email, but organizing in the future thematic EIC-related workshops, student exchanges, maybe postdoc positions, take money together, work with the Americans, of course, because there's the possibility to visit Brookhaven National Lab in Stony Brook, where there's a conference center whose most topics are related to the electron-ion collider. And so we have people from Mexico, Colombia, Brazil, Argentina, and I don't know if I missed a country. And so this is just the beginning. We're setting this up. There's, of course, also a lot of people who are from South America, but currently postdocs or students in North America and Europe. So it's basically setting the path for more fruitful collaborations within Latin America, contributing to this experimental and theoretical efforts in this field. Thank you very much. And
okay, thank you, Bruno, for your talk. One question, only one. No question, okay. The next speaker, please. Okay, our next speaker is Juan Andres of the university. The talk is about Hadron spectroscopy in the lattice QCD, basics, and some recent development. Juan?
To talk about lattice QCD, which has recently had a bit of a boom and can go hand in hand with theoretical and experimental efforts in QCD. So let's go right into business. Now, this slide became a bit redundant because of the previous two talks. I don't have to tell you again why quantum chromodynamics is not only quite interesting, but also quite complicated. So I will not go through the details. But I want to emphasize that it is indeed the name of the game in theoretical and experimental searches and studies of exotic particles. And now, to go into a bit more detail of actually what we are after, well, one of them, which is a bit of a buzzword lately, are glueballs, theoretically predicted as purely gluonic states from QCD. There are experimental candidates, a family of the scalar F-zeros, for example. However, up until now, there is no definitive, conclusive evidence to say this is a glueball, this is not a glueball. And a big question right now is, what is precisely a glueball in nature? Is it really pure glue, or maybe does it mix with constituent meson states, which of course share the same quantum numbers? And going more into detail, there are also the hybrid mesons. We saw in the previous talk a little bit about, for example, parity as a quantum number, but also charge conjugation, for example. In the naive QRQ, so quark anti-quark picture of the meson, there are quantum numbers that just cannot be had in terms of JPC. For example, the 1 minus plus, a conventional QRQ meson just cannot have it. There has to be an additional excitation that gives it the correct angular quantum numbers. And then this comes precisely from an explicit or valence, if you prefer, gluonic excitation. And this type of exotic quantum numbers, they are not only numbers that we know we can write down, but they have been measured mainly in the light region, these 2 pi 1s. In the charmonium region, there is still a bit of search for them. However, we've already found them in the light region. Why not in the charm heavy region? And on top of this, we have the XYZ states that have caused a bit of a controversy lately, where they have been experimentally found the states which again discard a conventional QRQ composition, even though we know that they are there. For example, this set 4430, it has a C bar C content, so okay, a little bit like charmonia, but it is electrically charged, which means that there has to be an additional quark, anti-quark in there of the light flavors to precisely give it the correct combination of non-zero electric charge. Or for example, the X3872, which has quantum numbers 1++, but an interpretation of a D star bar molecule is preferred over a standard meson. So the big question right now from theory and experiment is, okay, what makes up these exotic states? What are their internal dynamics and how can we understand them? There are a bunch of models, studies, etc. I want to focus on lattice QCD. And a big premise of lattice QCD for spectroscopy is the fact that you can measure the mass of hadrons, exotic or not, can also be a proton, for example, using basically random numbers. We know that we can calculate the value of pi with random numbers, but it's a bit of a leap to think that we can calculate the masses of particles with quantum numbers, but turns out that we can. So let me give a very, very brief introduction to lattice QCD. And really, for us as physicists, should not come to us a big surprise the fact that we can put theories on a lattice. We all know that we cannot discretize derivatives, for example, as finite differences. And in here, there is not much of a big difference with respect to this. We just take QCD, formulated on a finite 4-dimensional Euclidean lattice, not Minkowski. And this, through some theoretical details, will give us a non-perturbative and regularized approach to solve the theory. And now in our lattice, we will have the fundamental fields, so quarks, fermions, and gluons, and then we put them on the lattice, the quarks, just by evaluating them on the space-time points, while the gluons will live at the links that connect two neighboring points. So let me call the space-time point x, and then x plus a unitary displacement in one of the 4 directions. And in each of these links, we'll have an SU3 matrix that somehow represents the gluons. This is not directly the potential, the A mu, but it's related to it via sort of parallel transporter. The point is they represent gluonic degrees of freedom of the theory. Now, of course, we will have to define our gauge symmetry. So we have the local SU3 in the color indices. So we know how the quark fields have to transform. We know how the link fields have to transform. We can also define the gauge covariant derivatives, such as, the derivative acting on the quark field transforms like it should. This is kind of straightforward to do with these link variables. And now all we need to do to define fully our theory is basically define the action, right? And then this action, which of course has to depend, just as in a regular quantum field theory, on the fundamental fields, so our gauge fields and our fermionic fields. And then it will be expressed as a gauge part of the action, so F mu mu, F mu nu, F mu nu kind of thing, plus the fermionic part, which of course will include the dynamics of the quark fields and their interactions with the gluons. And this is, in a very simplistic way, precisely how the theory will look now. We have, 3D, because I cannot draw or find a picture of a drawing in 4D, which is easy. Now you have your lattice in here. On the lattice sides, you evaluate the quark fields, while on the links, we have the gluons, and you can have very complicated constructions. 2 quark fields connected by some gluonic line. You can have purely gluonic objects, like this square, which we call the plaquette, etc., etc. And if you want to know more details about why this works and how you need to define it, etc., etc., I've put some introductory references. For now, I just want you to know that you can define QCD on a lattice, and it will turn out that we can do a lot of things. So let's go and define the theory. First, the gauge action. It has to, of course, preserve the symmetries of the theory, and we would like it to recover the continuum gauge action that we all know and love. And even though there are many, many, many choices in the market, because you know that, for example, a derivative, you can discretize it in many different ways, depending on the order of the discretization error that you want. In here, it's exactly the same logic. We will use the plaquette, which is basically this square. It's a purely gluonic object. We will define the action, so some scalar quantity of the full theory that depends only on the gluonic degrees of freedom. It is ultra-local. It involves only nearest neighbors. And if you carefully take the limit of the lattice spacing to go to 0, so the 9th continuum limit, you will see that you will recover the pure gauge action. And because of the way that it's constructed, it has discretization errors of order 8 to the power of 2, which means as I go to the continuum, how fast am I recovering it? There are other options that involve more complicated shapes to reduce the order of these errors, but for now, to just know this definition will be enough. And already this kind of theory, so pure gauge, QCD, so to speak, is already quite useful for calculations, because in here, gluons are really the only states of interest in the complete absence of fermions. But real life has fermions, so we need to include them. And just like you might know from textbooks, then when you introduce fermions, the action looks something like this, with some Dirac operator in the middle. And of course, in the lattice, it will have to be some discretized derivative looking object. Again, there are many ways of defining it, and we use here the so-called Clover-improved Wilson fermions, which basically means that as we go to the continuum limit, we recover the correct fermionic action. We can reduce from order a to the 1 to a to the 2 the discretization effects by adding additional terms that in the limit a goes to 0 just vanish. We don't change the theory, but at finite a, they cancel discretization errors. Here I mark them as blue because as we take a goes to 0, this in here still becomes an integral, but these individual terms will become 0. This is a discretized version of just the standard Dirac operator, you know, the derivative, the gamma mu, natural units, the mass, etc., etc. Wilson means that we introduce this Laplacian-looking term for theoretical reasons that I will not go into detail, and the so-called Clover improvement comes here, again, vanishes when a goes to 0. It's a kind of Pauli-looking term with some discretization of the field strength tensor, and it basically allows us to have order a square discretization effects. There are other alternatives on the market, depending on which symmetries you want to keep, because several are broken when you go from the continuum to the lattice. Each one of them has advantages, but also disadvantages. In the end, you are free to choose. Now, generally, well, no, always in the continuum, well, when we want to characterize angular momentum quantum numbers, we work with SO3. But when you are in the lattice, you break this. It's not the rotations, all of the rotations are not symmetries of a square. Actually, you have to reduce the symmetry to now a subgroup, which is called the cubic group. Like the name says, it's just the symmetries of a cube. It has 24 group elements, 5 irreducible representations. It's still a subgroup, so we have a subduction, a reduction of symmetry. And now instead of working with, in the case of integer angular momentum, you know, 0, 1, 2, 3, etc., to label the irreducible representations of this group. Now we have only 5 irreducible representations. I have written them here, and how they reduce and how they relate to the continuum ones. The number in the parentheses corresponds to the dimensions, such that you see that the dimensions match. And then this means that there is a big difference between continuum angular momentum and lattice angular momentum. And the lattice angular momentum is precisely the angular momentum that is useful for the Hamiltonian that is in the background for the energy eigenstates. And then this reduction of symmetry, maybe with a bit of group theory, it can be known that now there is a one-to-many relations between the 5 irreducible representations of our new group and the infinite irreducible representations of SO3, which means that I cannot do a one-to-one mapping. I cannot say that something that has a given lattice angular momentum in the continuum will have, I don't know, j equals 0, because you see that this A1, the trivial representation, appears also in j equals 4. So there is a big labeling problem. A particle on the lattice that has some lattice angular momentum, for example, T1 with PC++, what are its continuum quantum numbers? Is it a 1 here? Is it a 3 here? Is it a 4 here? And there are mainly 2 ways to this identification. Either count degeneracies as you take the continuum limit, because then this subduction has to hold exactly, or we build creation operators for our particles on the lattice that somehow remember the continuum angular momentum that they had in SO3. Now let's continue with some other quantum numbers, because after all we have to have a well-defined theory. Well, linear momentum is kind of straightforward. It becomes a spatial momentum defined via Fourier transform. I don't think I have to go into a lot of detail here. We will work for now in 0 total linear momentum, so particles at rest. Parity and charge conjugation are pretty much like in the continuum, map x to minus x, similar to charge conjugation. And of course, flavor symmetry. You know that we can have SU2 isospin for degenerate up-down, maybe SU3 for up-down strange. You know, you choose whatever fits better. We know that in nature we are close to SU2, maybe not so much to SU3, but there are reasons to take these different symmetries. So in the end, particle physics in here is also, again, a game of symmetries. And now how do we do Hadron spectroscopy? Well, we have to create the states, and we have to make sure that they are close enough to the energy eigenstates, and then extract precisely their energies. So we will have some underlying Hilbert space where we can have creation operators that act on the very non-trivial QCD vacuum to create some state. And then, to analyze whatever this state is, we built Euclidean temporal correlation functions that you can see here with textbook in definition, including some kind of partition function, because in the end, because it's Euclidean, it's pretty much a statistical physics. And then since there is an underlying Hamiltonian operator that allows us to define the energy eigenstates, we have a list of energies. These states are a complete basis. We can put them in our definition, do a bit of algebra, and show that these 2-point functions give us access to what is called the spectral decomposition, which is basically an infinite sum of exponentials where each exponential contains the energy of the corresponding excitation of the quantum numbers that your state has. And of course, when we take time to be very, very, very large, we will have the contribution mainly of the lightest state, so the exponential that hasn't died off the fastest, and that will be the ground state energy of our set of quantum numbers, which means that if we measure these correlation functions at large temporal separations, we get the energy of the lightest energy eigenstate, which is great. If I want the lightest pseudoscalar, let's say with the quantum number, the flavor quantum numbers of the pion, then I would get the pion. But if it is a flavor singlet, I would get the eta prime, etc., etc. But this was only the ground state. What about excitations? Well, some very clever people figured out that to do this, you not only need to calculate one correlation function between two operators that are the same, but you can build a correlation matrix between different operators with the correct quantum numbers. Build your matrix, solve what we call the generalized eigenvalue problem, and the eigenvalues will have this exponential behavior that depends on the energies plus some suppressed contributions, such that if they are in the exponential, I can do a little bit of algebra with the logarithm to bring down what we call the effective masses. And the eigenvectors will tell us about the overlaps between the states that we create and the energy eigenstates that we are after. Because unless you know exactly what the energy eigenstates are, some very complicated functional of the fundamental fields, you must probably have non-zero overlaps with different states. This is a very powerful method, but we need to make sure that if we want to resolve, I don't know, 10 energy eigenstates, we need to have at least 10 operators, or else you don't have enough eigenvalues. We need to make sure that they are all sufficiently independent from each other, or else solving this eigenvalue problem is numerically unstable. And we need to make sure that all of the operators that we're using have significant overlaps with the states that we are after. Because if you choose operators that have all the overlaps 0 with the energy eigenstate that you're after, well, this will be by definition 0, and you will not be able to see it. So this was a bit of the introduction. Now, how do I measure these correlation functions in a realistic way? Well, we go to a path integral formulation, which, as we know, is quite useful. So this correlation function, we can write it in the language of the path integral, where we have the Boltzmann factor with our Euclidean action and our suitably defined partition function. Now, since we are in a finite dimensional lattice, we have a very large dimensional but finite integral that we need to solve, both over the fermionic degrees of freedom and the gluonic degrees of freedom. The fermionic ones are Grassmannian, which means that they satisfy anti-commutation relations, while the integral has to be over the group SU3, which is a very special kind of integration that involves the Haar measure. And we can start from this kind of integral, which looks very daunting, because these are all very non-trivial objects. This action you saw is quite non-trivial. These operators could be quite non-trivial. So in general, you cannot do it by hand fully. However, it turns out that if you divide it into first fermion or Grassmann and then gluonic integration, you can go a long way. So you define your fermionic, so to say, integration, where there are a lot of useful properties. The famous Matthew-Salam formula tells you that the partition function will just be the determinant of your Dirac matrix, and that the gauge integral that you are left with will be precisely with a Boltzmann factor that is only the gauge action, this partition function, which is just your determinant, and whatever came out of this integral that involves your creation operators. So we managed to simplify it quite a bit. And now we will focus on the term that is inside the integral that still depends on the gauge variables, but no longer on the fermionic ones. And in a very simple case with two degenerate quark fields and using the gamma-5 hermiticity property of the Dirac operator, this becomes basically 1 over the partition function, determinant of d dagger d, the Boltzmann factor. And this is a positive and normalized quantity. So we can interpret it as a probability density function. And then all that we learn about the statistical physics becomes very useful, because basically this correlation function becomes nothing more than an expectation value of some quantity that I have called A, that depends on the gauge fields, with respect to a given probability density function. Of course, this integral is still highly non-trivial. You just cannot do it by hand. But we are no strangers to hard integrals that we need to do numerically. And this is where Monte Carlo integration comes to the rescue. And in the context of lattice QCD, it's a world of its own, how you need to sample your probability density function in terms of these gauge variables. I will not talk about this, just know that it can be done. And then our expectation value, we can approximate it with this kind of estimator. So we are doing quite well. So now, okay, let's look at an actual operator. For example, the eta C on the lattice. This is a pseudo-scalar, so C bar gamma 5 C. And if we write down precisely this fermionic object that we need to do, is nothing but the operator at time 0, the operator at time t, creation, annihilation. We invoke Wick's theorem, which we probably are very familiar with, and it tells us basically that all of the fermionic degrees of freedom become propagators, quark propagators. And in the end, our very complicated expression basically becomes a bunch of traces. Traces of very big matrices, like the inverse, but traces nonetheless that we can calculate. And they have a very specific physical meaning. This was a meson propagating in time, the eta C, C bar C with pseudoscalar quantum numbers. So we have two types of propagation. We can have in time forward of the quark, forward of the anti-quark, or we can have quark, anti-quark annihilation at both times. And both are significant physically, so both need to be taken into account. So now, since we know D, in a way we can know the inverse, and now we have an expression that we can calculate in our computer. However, this is not the end of the story. D, the formula that I showed before, is very, very, very large. Millions of rows times millions of columns. It is very sparse, luckily, in our case, nearest neighbors interaction, because it's a derivative in the end. However, even though we have D and it has these properties, computing the inverse is just impossible. You cannot do this if the size is realistic enough. And also, even when the size is realistic enough, this means that you would have to store a very large matrix. This is a very well-known mathematical problem. And we are lucky because there are solutions, because it turns out that we don't need the inverse as a matrix. We just need the action of the inverse on a vector. Because if we want to estimate something like trace of the inverse, we don't need to know the whole matrix. Well, in principle, we only need to know the diagonal. But estimators such as this Hutchinson one allows you to take just suitably chosen random vectors and then calculate the inverse times the random vector, inner product with the random vector, update your average, get an estimate of this inverse. So how are we supposed to do the inverse acting on a vector? Well, this is equivalent to solving dx equals b, so solving a linear system. At some point, we'll learn how to do it, but we are more used to Gaussian elimination in a, 3x3 matrix, but this is millions by millions, so it's unfeasible to do it directly. Luckily, there has been quite some developments over the decades on how to solve these problems, and a very famous one that comes from numerical linear algebra are the concept of Krylov subspace algorithms. The famous Cayley-Hamilton theorem tells us that D inverse is a polynomial of D, if it exists. And therefore, it is a good idea to build an approximation to the solution in the span of the vectors that are precisely a polynomial of my matrix, which is called the Krylov subspace. And now, depending on the properties of your D, there are different methods that you can use. These are just iterative algorithms that you can just let run, and you will find an approximate solution. And then I have put in here a reference to some introductory explanations to this topic. So just the presence of this kind of problem makes lattice QCD very important, not only for physics, but for numerical linear algebra. It is a bridge between physics, applied mathematics, and because of the sheer size of these matrices, high performance computing. You need to be able to calculate D acting on a vector in very efficient ways. And this is not the kind of matrix that you just put in Python explicitly and just apply to a vector. And for that, we need supercomputers. I am showing you here the examples of SuperMOOC and Fritz that are in Munich and Erlangen in Germany, and they are very often used by the lattice QCD community to generate these Monte Carlo samples and also solving millions of linear systems, because this is very expensive to do. Also thousands of matrix multiplications that we need to do, and everything needs to be incredibly efficient because these are expensive machines. So each second of computation in here needs to be taken the most advantage of. So of course you have to do everything very optimized numerically. So let's go back to spectroscopy. A big advantage in lattice QCD, as I mentioned before, for example, I know quantum numbers that I want to study. I don't know, something, let's say, normal like a pion, or something exotic like this exotic pi1. While in experiments, of course, you have to make sure that you collide particles that allow for the kind of new particle to appear that you want to study. In lattice QCD, we have a very big advantage, which is that we can create our creation operators with whatever physical features, quantum number, spatial extent, etc., that we think they should have. For example, the exotic 1 minus plus, we know cannot be purely Q bar Q. We make it a hybrid meson by putting some explicit gluonic excitation in between them, which is proportional in a way to the field strength tensor, and what's more gluonic than the field strength tensor. So we can obtain the quantum numbers that we want, and this means putting a valence gluon. So a vector meson times this valence gluon can give you, well, the whole decomposition, but among other things, precisely the exotic quantum numbers that you want. It can also give you non-exotic ones, so just as you the scalar. For example, this one, the ground state is, let's say, for the correct flavor quantum numbers, the pion, probably not much gluonic excitations. So we want something that doesn't have explicit gluonic excitation. We can go with this. Some excited state could be a hybrid from the supermultiplet, so we can put gluonic excitations. We can also look at non-exotics, for example, the 4 minus plus. We don't need this gluonic excitation. We can just put a standard derivative. And a little bit of group theory, which is actually quite fun to do, allows us to build operators for any set of quantum numbers, forbidden or not. We are not limited by the restrictions of the quark model. What about gluons? Because I mentioned them. Well, in there are no valence quarks, so we need something that is purely gluonic. You remember that the gauge variables live in between the links. We need a color singlet gauge invariant object. Well, we can take the trace of the product of the links along a closed path like you see in here. These objects generate a reducible representation of the cubic group. What does that mean? That we can build from them creation operators with fixed lattice quantum numbers. This is all very introduction to theoretical particle physics, but on the lattice. It has the advantages of being very cheap to compute. Each one is just a 3 by 3 matrix, so this product is cheap. You can use any shape to mimic any kind of a spatial structure, and they mimic precisely gluons on the lattice. However, there is no free lunch. There are disadvantages. They are very statistically noisy. Remember, Monte Carlo. And if we want to have good statistical signal, we need 10 to the 4, maybe even 10 to the 5 Monte Carlo samples to get a good signal. And in a theory with dynamical quarks, they are incomplete in the sense that, well, if there are dynamical quarks, and they are probably mixing in there, and this has no valence quarks, so we should also include them. But nonetheless, they are good operators in a sense. So now I mentioned about physical-looking creation operators. For example, this Q bar Q construction. But we know that probably in nature, these particles that we study, they are not point-like. They are composite hadrons, and therefore can have some kind of a spatial extent. We mimic that on the lattice by making sure that our new fields are smeared. The smear field at position X has some contribution from the original field at all positions. with, of course, a suitably chosen physically relevant smearing function. We use what is called distillation, which is basically say, I am after the low modes, the low energy modes of the theory, and what's more related to energy modes than the Laplacian. So we define the eigenvectors, the lowest eigenvectors of the Laplacian, well, the lattice gauge covariant Laplacian, of course, and we create this projector operator that acts on the quark fields. So now our new Hadron creation operators are built with these distilled, so to say, fields. This method was improved back during my PhD, where now this projection operator becomes more like a restricted modulation, but the principle is exactly the same. And again, you have two kind of physical phenomena, connected propagation in time, disconnected quark-anti-quark annihilation, with now new matrices that you can see a definition here, are not as big as the inverse, not millions by millions. Now a bit more like hundreds by hundreds, which means that calculating traces suddenly became very easy and very cheap. And on top of that, even though now we have to do plenty of inversions here, we can save them and use them later on. And now, because a picture speaks louder than words, here I'm showing you precisely how we extract the energies or the masses as a function of time. You saw from the explanation that as time goes to infinity, I should get a constant, and that is precisely what you see in here. So for example, for the pion, which is the cleanest signal, for the eta prime, it's noisier, for the eta c in red only with the connected contribution, in black with the connected and the disconnected, and finally the Wilson loops, which you see are the noisiest of all, even though they are all in the same JPC. So a very famous thing in here that you can immediately see is, yes, we get our energies, but they are very noisy. We have an exponential signal-to-noise problem that we need to tackle. The gluonic operators are much noisier, that's a big problem, and the inclusion of quark-anti-quark annihilation brings a lot of statistical noise. So we need to tackle this in a way, as well as the fact that this approach to a constant, it takes some time, you can see. And this contamination in here comes precisely from the additional terms in this spectral decomposition. Here is another example now of exactly the same channel, but using different creation operators. One with no derivatives, one with derivatives, one with two derivatives, with a bit of a gluonic content in here. And then you see that they all eventually see the same state because they have the same quantum numbers. They have to see the same state, but the rate at which they converge to the flat region is much different because some of them are more physical looking than the others. So they need some more time to approach the ground state. So this is all a game of sort of Lego building that we have to play in Hadron spectroscopy. And just to mention, because there was a mention of how there are some types of mesons, for example, these heavy light ones like B, which are a bit of a problem, but they can be tackled on the lattice. Heavy light mesons such as B, or if your light mesons, if your light quarks are sufficiently light, the D mesons, we treat them as a static light mesons, which means that the heavy quark only propagates in time. And after you do that, you can play exactly the same game, extract your energies, and the flat region gives you the energy in lattice units. This is ongoing PhD work of our PhD student. So some applications to make sure that this becomes relevant in the context of what everyone is doing, mapping the low-lying meson spectrum, including quantum numbers. This has been done quite systematically. A study of potentials, also hybrid between a quark-anti-quark pair. This is very relevant for string breaking, so something very specific of QCD in terms of the gluonic string. Static light mesons, as I mentioned, charmonium scattering can be done on the lattice. Exotics like tetraquarks, pentaquarks, more buzzwords like the G-2 calculations can also be done on the lattice. And this shows in a way that this is a crossroads between particle physics, applied mathematics, and high-performance computing. So if you like particle and statistical physics, parallel programming, and high-performance computing, and numerical linear algebra, this is perfect to do research because it all comes together with results that are very relevant for today's research. Here is a bit of a picture that I took from somewhere that shows more or less the procedure that we do. We start from our supercomputers, simulate the particles, get an energy spectrum. And then you say, okay, is this useful? Can it be compared to nature? And the answer is yes. Lattice QCD is a highly non-trivial test of QCD from first principles. For example, with only some input parameters, we can test precisely how, grossly speaking, how well defined is QCD in terms of the action or the Lagrangian. And in here, I'm showing you the charmonium spectrum taken from the PDG, so our world, compared to the lattice calculation that was done during my PhD. And then you see that there is remarkable agreement between all of the charmonium states that we decided to measure, and we didn't put as input parameters all of these masses, or else it would be like a circle, right? With only some few input parameters, we can do very powerful that are predictive and post-predictive calculations. So lattice QCD is quite powerful for this. And now to finish in these 10 minutes, I want to show some results that we are doing in our search for the scalar glue. This is done in the context of this research unit, future methods for studying confined gluons in QCD. It's bringing together mathematicians and physicists from these 3 institutes to tackle well-known problems in Hadron spectroscopy. Good creation operators, good generation of cage configurations, Monte Carlo sampling to reduce the statistical error, more efficient solutions of these linear systems. And this has been done in collaboration with the gentleman that you see here. So just to put this into a bit of a context, glue balls are flavor singlets. We can define flavor singlets. We take SU3 flavor symmetry. So we need to, well, we know that we have hypercharge, isospin third component as quantum numbers. We're looking for the scalar flavor singlet. But the problem is that there are several of those. Light mesons like the F0s are that. Charmonium is that. A scalar glue ball can be that. A singlet 2-pion operator can also be that. Anything that group theory tells you that can be is. So there is still too much symmetry, and we cannot really tell them together, tell them apart, who in my spectrum is a light meson, who is charmonium, who is a scalar glue, etc., etc. Why can't we do that? Because our lattice creation operators that have the correct quantum numbers, when they act on the vacuum, they create something. But this something will have non-zero overlaps with all of the energy eigenstates. I just mentioned the first few, but of course there are infinite. And then since all of these overlaps can be non-zero, there is no symmetry that makes them zero, it means that if I take, for example, a charmonium creation operator, acts on the vacuum, I say, okay, what is its overlap with the F0, so not charmonium? If this is non-zero, then the ground state that I will get from my charmonium correlation function is the energy of the F0, not of the chi-C0, which means that energies obtained from charmonium are not necessarily charmonium eigenstates, or charmonium operators are not specifically charmonium eigenstates, which means that we need to take all of this into account. And there is a golden rule. If you want to access a state, you must be able to resolve everything below it. If you want to know about heavy charmonium, you need to know about everything that is below, so the full light sector. This is related to a famous mixing problem in the real world, where of course SU3 is broken, but we still keep SU2, where these F0s that have been measured, so let me call them the mass eigenstates, are related to these flavor symmetry eigenstates, but also composition eigenstates in a non-trivial way. There is a rotation. So there is a pure U bar, U d bar d, pure S bar S, pure glue, but that they mix together to form the F0s. So the physical states are not pure constituent states, but a mixture. So the scalar glue ball that I mentioned before is probably not pure glue, but a mixture with constituent states. So how can we map this spectrum? Well, it's kind of easy. We built our meson operators on the lattice, our gluonic ones that I showed you before. 2-pion operators, you just need a bit of group theory, you know, Clebsch-Gordan coefficients. And then we can build a mixing matrix between the different types of operators with each other. And now, diagrammatically, this is what you will see. So for example, light mesons, you know, Q bar Q, they can propagate together or annihilate. Same with charmonium, but they can talk to each other through loops, which, because of the OCI rule, is believed that they are suppressed. But you can also have the 2-pions, which of course, since they include light quarks, they talk directly with the light. Okay, yeah, no, so after getting pressured by Zoom, so let me move on. So for example, the 2-pion will include more complicated propagation, because now there are, you know, 4 quarks, okay, 2 quarks, 1 antiquarks. So the diagrams that you can get are more complicated, and the glue balls talk to everyone via disconnected loops. So now we're going to measure this, and another very big advantage in lattice QCD is on less experiment, where you can only do experiments in a real world. You cannot change the mass of the pion. You cannot say, it's too light for me, I want to make it heavier. But in lattice QCD, we can. We can set some input parameters, so some physics of our universe that we're simulating it, to put ourselves in more convenient scenarios. I create in here 2 different scenarios, so lattice sizes, but I want you to look at is the pion mass. None of the 2 are the physical one. It's just that one is much heavier than the other one, but both are heavier than the physical pion. So you ask me, why do this? You are significantly far away from nature. Yes, but there is a prediction of the scalar glue ball at around 1800 MeVs. And we know that it could decay into pairs or groups, or even groups of pions. So I want to study this in a systematic way, but first I would like to just see the 2 pion decay, be a heavy pion mass, to push up the threshold, and then push down the threshold to see also the 4 pion decay. So we can make the problem easier by having control over the physics of the world that we simulate. And then I will just show you precisely the energy spectrum that comes out from considering all the different types of operators, first separately, then together, and see if they talk to each other. For example, charmonium operators create states that are similar to the light region. What happens when I put light and charmonium together? Do gluonic operators mix with each other? Do 1 particle and 2 particles mix with each other? These are all things that we can directly see. And this is precisely how you see it. At the fixed time t = 1 jump in time, I am showing you the correlation matrix between charmonium, light meson, 2 pion, gluonic for the 2 pion masses, and you can immediately see that there are off-diagonal entries. States that are built from charmonium creation operators talk to the ones that are built from gluonic operators or light meson operators because of this mixing. There is not enough symmetry to tell them apart. It doesn't automatically block diagonalize. That would be ideal. So you cannot look at the different states separately. You need to look at all of it and then disentangle. And this is what I'm showing you here. The effective masses for ground and then excitations as you go up the ladder. First only light mesons, then only charmonium, then together, then with gluonic operators, with some reference lines of the non-interacting 2 times pion mass, 4 times pion mass, the prediction of the quench glue ball. And then the first thing that I want you to notice is that charmonium operators see a state that is consistent with the light ones. This immediately tells me that the charmonium operators create states that have non-zero overlaps with, for example, let me call them the F-zeros. So this flavor mixing that in the literature is quite often neglected is completely relevant. And it only happens because of charm annihilation effects. So OCI should not be an automatic argument to say I can neglect disconnected interactions. Because when I put them together, then the spectrum becomes clean again. And now this first excitation of charmonium, which is actually consistent with the Chi-C0, remains. However, this wobbly state becomes absorbed by the light mesons. So we really needed to include that. We now include the gluonic operators, no change in the spectrum, which tells us that whatever these states are, all of them probably have some gluonic component. And now finally, I put in together the 2 pion operator, and it creates a new additional state in magenta. Hopefully you can see colors here. And now I can show you the overlap, so very quantum mechanics kind of construction between the states created by our operators and the energy eigenstates, color-coded via this spectrum plot. And then you see that for 3 charmonium, 5 light meson, 1 2 pion, 1 gluonic, everyone sees a little bit of each other, but really this new state mainly comes from including the 2 pion operator, which helps us avoid this problem that I mentioned before, that if you want to resolve your states, you need to have good creation operators. Now we can repeat exactly the same with the heavier pion mass, so everything is pushed up, but the principle is still the same. Charm annihilation effects allow you to see a light state even with charmonium operators. So SU3 flavor of singlet mixing is something that is happening, and when we put them together, everything becomes much cleaner. and the 2 pion operator still brings something new to the picture. So what do we learn from this, which is a first step in our calculation? That the mixing that happens via the disconnected contributions that are OCI suppressed allow us to see light states which are harmonium operators. The explicit mixing, the off-diagonals of our matrix, are non-negligible. Gluonic and mesonic operators mix with each other, and we need to include multiparticle states to avoid missing energy eigenstates that are actually there. I don't have to tell you that, of course, 2 pion states exist, but if we want to be able to measure them, we need to have 2 pion creation operators. How can we improve? Long story short, as I said, the golden rule: saturate the spectrum. If you want to see the 10th excited state, you need to be absolutely sure that you can clearly see the 9 ones below that. And of course, as with everything statistic, reduce the noise. So now for a closing note, I just want to say that the first part of the talk, which was introductory, I skipped a lot. So this was by no means comprehensive. And even though I focused on spectroscopy, lattice QCD has many more reaches. For example, the alpha collaboration is called like this because it determines the alpha, well, the alpha S, the running coupling constant, with results that are quite competitive with other non-lattice calculations. And there are many, many more applications to lattice that come from not only these collaborations that I have put in here, but many others. And all of them share both computer and human resources. And, well, a bit of a Christmas wish, and also a big reason why I want to come here, is because it would be great if Colombia, that already contributes to a lot of effort in physics, of course, can enter the game in lattice QCD. Because via collaborations, we don't need to have, I don't know, the supercomputing labs that, for example, Germany have. We don't need to have them. We need to have collaborations. We need to have the will to collaborate, and we need to be open to the new advantages that lattice QCD can bring us. So thank you for your attention.
Juan Andrés, thank you very much for your presentation. You need some help?
No hay preguntas. A las 2:30 en la sede Vipri. Bueno, preguntas sí pueden haber después en la sala. Ya los que vean allá ese peón de 420 MEPs le pueden preguntar. Y esto, sede Vipri, no olviden, ¿ok? 2:30 sede Vipri. Se corre todo. Media hora ya está en la actualización, ya pueden ver ahí. ¿Listo, señores?
Maybe